the moment of inertia of this strap about the axis of rotation, which is the way I'm flipping it around, a vertical axis. Okay? You get by simple integral of mass density. Of course, we got holes in this thing, but imagine it's a uniform rod or something, or a rectangle. You've got formulas for moment of inertia. We're not requiring you to integrate to get moments of inertia, even though we could because you've had enough calculus. Okay? Textbook doesn't do the integrals. And the integrals are not difficult. You've done moment integrals. Every calculus course does moment integrals. If you didn't do moment integrals, you didn't have a calculus course. And of course, your teacher was one of my former students who kicked my butt. If that turns out not to be true, and I don't really mean it. But because I know he does a good course, real good course. Okay, so anyhow, you got that moment of inertia. It tells me how much work I've got to do to get this thing up to whatever angular velocity. Because it tells me how much kinetic energy change there is between here and here. If I just know that final velocity and the moment of inertia, I can calculate its change in kinetic energy, rotational kinetic energy. Okay? Now, if I want to measure the moment of inertia of this thing about some other point, well, I could measure it around the end. Now, right here, I'm measuring it around the center of mass. Okay? So we did see something on the homework where somebody thought, well, the moment of inertia about the center of mass has to be 0, because that's the middle. Okay? Well, moment of inertia isn't that. The person did a really good job finding centers of mass and so forth, and just got a little confused about definitions. So you got this. You got to add up all the MR squareds, and there are no negatives to balance any positives, right? All the MR squareds of every particle could be 0 if it's right at the center of mass. Other than that, it's going to be non-zero. Okay? So you have the problem of figuring out the moment of inertia of one of these things. You do have a formula, but I think I restricted you to certain given information in that problem. I'm not sure. Maybe I didn't. Okay, anyhow, if we want to measure the moment of inertia of this thing about some axis over here, okay, then what do? Well, see, this thing might be in motion as well as rotating, right? So here it goes. It's got a moment of inertia. Every particle has some distance from the axis at any given time and some angular velocity with respect to this axis. Angular velocity just being its speed divided by this radius with a sign around counterclockwise and stuff. But there's the concept, okay? So how would you calculate the moment of inertia here? You could integrate easily enough to get the moment of inertia of this thing, but how would you get it about this point, considering that it's moving maybe along a straight line, which would make the moment of inertia constant, okay? Well, the way you do that is use the parallel axis theorem, which we talked about a couple of weeks ago. Okay? It's just the moment of inertia a particle would have if all the mass was concentrated to the center of this thing, at the center of mass. It's the moment of inertia a particle of that mass would have at whatever speed this thing's moving, regardless of its rotation, plus the moment of inertia it has about its center of mass. Okay? Now you want to read the full statement of that theorem, but that's the idea. You treat this thing about this axis as a particle with all the mass concentrated at the center, you get its moment of inertia. Then you get its moment of inertia about the center, and now you've got its total moment of inertia relative to this axis. Okay? And you need that for some of the problems I've already assigned.